Alright, so welcome back to your favorite inorganic tutor YouTube channel once again. Today is another episode. Alright, before I begin, let me give a very big shout out to Mr. Rad, Mr. Enoch, and then you watching as well. Everyone watching out there, God really bless you. I really appreciate your time whenever you press on my content to watch. Thank you very much. So we are going to look at Leibniz theorem. You know, this theorem, we use it in calculus whenever we have two functions and then one can be differentiated to the nth derivative, right? So this theorem really helps. We really appreciate the effort of Leibniz in calculus, right? So Leibniz really give us some theorem and it is so helpful in calculus workings, right? So today, that is what actually we are going to look at. It's a very helpful theorem. So the Leibniz theorem. The Leibniz theorem. So the theorem is all about when you have a function, two functions, and one is not able to differentiate to a constant unless you use the nth derivative. That is where the Leibniz theorem comes in. So this theorem is all that I'm talking about is just a simple theorem that you have to know. Today is just about computation. The next time I'll come out of how he came up with the theorem. So today I want to just give you the theorem and then we use it to solve some particular problems, right? So this is the theorem, how it goes. So this is the theorem of Leibniz, right? So it says that whenever a function is differentiated, one function is differentiated to a constant and then the other one can be differentiated to an nth derivative, then we use his theorem. So his theorem says that the nth of the combination of what? 0. You know that this right here will be 1, right? And then you multiply by the first function times the second function n, then plus nth combination 1, u1, then vn1 plus n combination 2, u2, vn2, right? Then this goes up to n combination r, vn minus r. So this is a theorem for Leibniz. So he combined a combination and then differentiation as well. So we are going to look at a problem to clarify this theorem, right? So let's look at this particular problem where it says that we should find the yn, right? We are going to find yn if y is equal to x squared sine x. So you know, in our normal mathematics, basic calculus, you not have this right here, because when you have this, it means you have to differentiate. You know, when it comes to product rule, it means that you can differentiate all the two functions completely, but this case you can differentiate this to a constant, but this you cannot differentiate it to a constant. So that is where the Leibniz theorem comes in, right? So the Leibniz theorem states that we should check out, or we should say that the first function, right, we should consider the first function to be differentiated to a constant. So the first function must be able to differentiate to a constant, and that is why we have x squared right here, right? So we have to be able to differentiate this two of these functions, one of them to a constant, so that we choose the other one as our second function, and that one will be differentiated to an nth derivative. So I want you to consider this particular note before we continue, right? So he says that Leibniz says that if y is equal to sine n, if y is equal to sine n or sine x, then we can say that if y equal to sine x, then the nth derivative of sine x is going to be sine into pi over 2 n plus sine into pi over 2 n plus x, right? And then if y is equal to cos x, then we can say that yn is equal to cos into pi over 2 n plus x. So this is the conditions he gave. So you have to note these conditions so that you can work with Leibniz. He says that if y is equal to sine x, then we can say that the nth derivative of sine x is going to be sine into half of what? The pi times the n plus x, right? The same thing, likewise, the cos aspect as well. So let's consider this particular problem and work it out so that we can solve the problem and understand the concept very well. So let me erase it. Let me erase this and begin the process. Begin the process. Right, so Leibniz theorem. Right, so we all know the theorem. The theorem is just a formula that you have to do. The next time we will come out of to how the theorem came about. But right now we are going to focus on how we can do computations on one problem of the Leibniz theorem. Right, so this is the theorem. It says that if a function, one function can be differentiated to an nth derivative, then we can consider the next one that we can differentiate it to a constant, and the formula is written in this form, right? So we say that nth derivative, n combination 0, then un, u, then vn, right? Plus n combination 1, u1, vn minus 1, plus n combination 2, u2, vn minus 2. This continues up to n combination r, vn minus r. And this is the theorem. And so we are going to consider this particular problem as to how we can solve it. Find yn if y is equal to x squared sine x. Right, so this right here, we have to consider the first function to a function that we can differentiate to a constant to get a, we can differentiate down to a constant, right? So we say that our u, we let our u equals to a, s squared, right? So we differentiate this to a constant. So we say the first derivative, which is u1, is going to be 2x right here. Then the second derivative is going to be what? 2. We differentiate this and then we get 2. And then, now that we have considered or we have identified our function that we have been able to differentiate it to the nth, to the constant, then we identify our nth derivative, which is the sine x. So we can say that our v is equal to sine x, right? So our v is equal to sine x, and that is very simple. So we use that. So we move on and we say that since following the conditions that Leibniz gave, he said that if y is equal to sine x, then we can say that yn is what? Sine into half of pi, then times n plus x. So over here, we are going to apply the same knowledge, and we can say that we have Vn equals sine into pi over 2n plus x. Right, so this is our Vn. Right, so what next? What we have to look for is by using the theorem. So we have to consider the theorem right here, then we can go. So this is the theorem. So we just have to fix in the solution that we have, and we are good to go. So right here we have yn is equal to n combination 0. So n combination 0, u right here is s squared, right? And then Vn right here, sine into pi over 2n plus x, then plus n combination 1, u1, which is 2x, times Vn minus 1. So this is the Vn minus 1. So we have to subtract 1 from the n. So we have sine into pi over 2 n minus 1 plus x. Right? The next one is going to be plus n combination 2 u2, which is 2. Then Vn, which is going to be sine into pi over 2 into n minus 2 plus x. That is very simple. So we simplify this, and then we can get our yn out of this function. So we have right here is going to be yn is equal to n combination 0 is 1. So we have s squared sine into pi over 2 n plus x, plus n combination 1 is n, right, times 2x sine into pi over 2n minus 1 plus x, plus n combination 2 is n into n minus 1 all over 2 times 2, right, into, then we have sine into pi over 2 n minus 2 plus x. Very, very simple. So we have right here our solution. So we are going to have y this n is equal to s squared sine into pi over 2n plus x, plus this right here tends to 2nx sine into pi over 2n minus 1 plus x, then plus this right here cancels this, so we have n into n minus 1, then we have sine into pi over 2 n minus 1 plus x. And this becomes our final answer to this particular problem. It's very, very easy. What you have to do is that you have to consider the theorem, and then you follow the theorem. You get right to your destination. Thank you very much, ladies and gentlemen. This is the solution to our problem. Bye.